Here I'm in the Garden Museum, and actually I'm in Paris to give a invited paper at the Sensometrics conference. I'm here at the Institut Pasteur in France, in Paris, and I'm about to give my talk here, my invited talk on compositional data analysis and a link to correspondence analysis at this conference of Sensometrics 2024. So I've recorded it again, and here it is. My invitation to the conference Sensometrics 2024 was to talk about compositional data analysis. Compositional data are not found, as I can best ascertain, in the area of sensometrics. However, it is true that correspondence analysis is used in both sensometrics and compositional data analysis, so there lies some connection, and explains my title. And I'm discussing data on the chemistry of seafood, so at least my talk is related to food research, and food chemistry might well become an important issue in sensometrics. Now, I often start talks with a limerick. In this case, you're going to get 3. And these limericks summarize my whole talk. Compositional data can be fun. Their numbers always add up to 1. Drop some categories and re-express. The data change. It's a mess. Rather use log ratios, then you're done. Correspondence analysis is also much fun, though its numbers don't add up to 1. But counts you should relativize and remove the effect of sample size. Which method is better in the long run? Now CA with power transformations, I hope will get your admirations. With zeros it can cope. Can the log ratio transform? Nope. I'll illustrate this on fish and crustaceans. Compositional data are non-negative multivariate data, where the absolute values of the data carry only relative meaning. Such data are found in many areas, especially in chemistry, geochemistry and biochemistry being 2 prime areas, but also in the rapidly expanding fields of genomics, microbiomics, metabolomics, proteomics, in fact all the omics areas. Because the absolute values are not of interest, compositional data are often data with a constant sum constraint. That is, the values for each multivariate sample are either observed as summing to a constant, usually 1 or 100%, or are expressed as values relative to a total that is irrelevant to the research objective. For example, the composition of a chemical sample, or the various ingredients of a certain food, recipe, or even a cocktail. So here's a nice sensometric experiment. Vary the 3 ingredients of a Negroni cocktail and get respondents to express their feelings. In my case, I might prefer a bit more gin and less vermouth. I present here the 3 giants of compositional data analysis, or CODA as it's called. From the right, Professor Jean-Paul Benzicry, one of my thesis advisors in the 1970s in Paris. Then Professor John Aitchison, Scottish statistician, who is regarded as the founder of CODA. And then Dr. Paul Lewy, Belgian molecular biologist, one of the founders of the discipline of chemometrics, who anticipated most of the ideas in CODA a few years before Aitchison, but published them originally in medical journals. I may be the only person who knew all 3 quite well personally. I have published with all 3 and spent a significant amount of time with them, especially with Lewy. Here are some of Lewy's original publications in the mid-70s. Compositional data can be parts of a total that is also relevant, which I call the size of the sample. On the left, you see the daily total kilocalorie intake of an average German over 60 years, or on the right, the total annual world fruit consumption over 60 years. In both cases showing the changing compositions of that consumption, which is the shape. I deal with these concepts and their relationship in this article in the Journal of the British Ecological Society. And I also have a video summary that you can find easily on YouTube. But in the present talk, I concentrate on the compositional parts, that is, the shape of the multivariate sample. So why do compositional data need different treatment? It's because of a principle Aitchison called subcompositional coherence. If you have a composition and add or take away components called parts, then when you reproportion the data to sum to 1, the data will change. This is usually illustrated with small data sets, which exaggerates the problem. Like this example from my own book. Here are data on 4 fatty acids in certain proportions. When you take away 1, the last one here, as if you never had it, then the proportions of the first 3 will change. You can see that the correlations between the first 3 parts are different, depending on which data set you are analyzing. In the 4-part composition, the correlation between 18,4n-3 and 25n-3 is 0.357. But in the subcomposition, this correlation between the same 2 fatty acids becomes minus 0.139. Hence, correlations are subcompositionally incoherent, and methods such as PCA, which analyze covariances or correlations, are affected by this. Correspondence analysis is also incoherent in this sense, since it analyzes row profiles, the rows of data relative to their total. But as I show later, CA is more coherent than one thinks. Also, it has to be said that when the number of parts is very large, as in the omics areas, the incoherence is very much diluted and much less of an issue. A solution to this dilemma is to not use the original compositional values, but their ratios, since these are invariant to the composition being reduced or extended. So in the upper table you see the 6 ratios formed by the 4 parts in the original 4-part data set, and in the lower table you see the 3 ratios of the 3-part data set when the 4th part is eliminated, and you can see they are exactly the same. So these ratios are log transformed to get log ratios, which have several convenient properties, such as log A over B is minus log B over A. Log ratios make sense for the interval scale-based methods of statistics. So in fact, the only special aspect of CODA is to make a log ratio transformation of the data and then carry on as before, with all the usual statistical methods of unsupervised and supervised learning. But which log ratio transformation must we use, since there are several, and how are results using log ratios interpreted? Here are the most useful log ratio transformations. Of course, now we have to assume that the data are strictly positive, which is a thorny issue in CODA that I will come back to later. The first is the simplest, the pairwise log ratio, or PLR. For a composition with J parts, there are half times J minus 1 unique pairs. So for a sample of size I, all the PLRs are in a wide matrix with I rows by half J minus 1 columns. But the rank of this matrix is only J minus 1 because of all the linear dependencies amongst the log ratios. Then there's the additive log ratio, or ALR. A set of ALRs are J minus 1 PLRs with the same denominator part, called the reference part. So the reference part, the denominator part, is fixed, and we have J minus 1 PLRs with respect to that reference part. Since there are J potential reference parts, there are J different sets of ALRs, and each has rank J minus 1. Finally, there's the very useful centered log ratio, or CLR. This is the log ratio of a part relative to the geometric mean of all the parts. In other words, the log of the numerator part centered by the average of the logs of all the parts. In an I by J matrix of the log transformed data matrix, the CLRs would be the matrix centered by the row means. There is just one CLR transformation of J CLRs, and their rank is J minus 1. So they have one linear redundancy since their sum is equal to 0. This redundancy presents no problem for using them in multivariate analysis. For example, If the inverse of their singular covariance matrix is required, we just use the generalized inverse. Notice how all these transformations have rank J minus 1, one less than the number of parts. And the original compositional data matrix X also has rank J minus 1, since the rows all sum to 1. Here are the three possible log ratio transformations again, just to point out that all three are useful for unsupervised learning, especially the set of J CLRs, since they are equivalent to all the PLRs. CLRs are generally not used for supervised learning, where variable selection is important, so CLRs are not used since they include all the parts. The data sets I will use to demonstrate how CODA works are taken from this database from the United Nations Food and Agriculture Organization on the different sets of nutrients in seafood, both fish and shellfish. Because of some data not being available for certain species, I restricted myself to 23 species, and I will be analyzing the mineral and fatty acid compositions. To show the difference between the original data and then the compositional data, here are the 23 species ordered row-wise in descending order by the total of the 9 minerals in units of milligrams per 100 grams edible portion. The minerals themselves are ordered in ascending order from left to right, and the top 6 elements are easy to see, but the rarer elements, copper, iron and zinc, have such small values that they are hidden on the left. This figure includes both the size and the shape of the data. Now the compositions are shown, showing only the shape in percentage units. This figure gives a different view of the data, but notice that the ratios, and thus the log ratios, are identical in both cases. So whether we used ratios of the original data, not as percentages, or as percentages, we get exactly the same numbers. The log ratios encapsulate the shape information, no matter how the data are rescaled. But still we don't see the 3 rare elements on the left. So here's a zoom on the thin range of data on the left from 0 to 1%. This shows European oysters to have the highest percentage of these 3 rare minerals, and the 2 cod species the least. If we redefine these 3 minerals as percentages of the totals of just these 3, then we'd have a subcomposition with rows again summing to 100%. Once more, the log ratios in this 3-part subcomposition would be identical to the log ratios in the full 9-part composition of all the minerals, since they show perfect subcompositional coherence. Here are 2 different dimension-reducing analyses of the same data matrix. Correspondence analysis, CA, on the left, and what I call log ratio analysis, or LRA, on the right. CA is well known. LRA is the PCA of the centered log ratios, the CLRs. And since the CLRs are the row-centered log transform data, and PCA then centers the columns, log ratio analysis, or LRA, is the analysis of the double-centered log transformed matrix. One reason, however, that explains the difference between these 2 results is that CA weights the parts, the minerals in this case, proportionally to their marginal proportions, whereas LRA, as generally applied, does not. Lewy knew about this weighting because he had visited Paris in the 1970s to have some meetings with Benzicre's group. So he introduced the same weighting system into log ratio analysis since it suited his application to biological spectra, and he called this the spectral map. So if we weight the parts in log ratio analysis, that is, do a spectral map, which I also call the weighted log ratio analysis, the solution is more like the CA one. But soon we'll see how closely connected the CA solution is to the regular LRA. But to weight or not to weight, that is the question. Well, for this talk, this is another question, which I'll leave to another time and place. For the moment, we use LRA in its unweighted form, which is what is generally being done in practice. I will come back to the analysis of the mineral data soon, but now I want to skip to the other data set, the 15 fatty acids on the same species. Fatty acids make a nice application because they have 3 natural amalgamations, and when these are summed, there are no zeros. Saturated fatty acids, monounsaturated fatty acids, and polyunsaturated fatty acids. Pairwise ratios of these 3 are routinely reported in research articles, and because they are 3 and they sum to 1, they can be plotted in a ternary diagram. The distances between the species are Euclidean distances between their compositions. For many reasons, the Euclidean distance is not the best for showing such between-species differences. But here we can at least see the simplex compositional space for 3-part compositions, and for bigger compositions the space is expanded into many dimensions, a regular 3-dimensional tetrahedron for 4-part compositions, and in general J-1 dimensional simplexes for J-part compositions. Let's now look at the CA and the LRA biplots of this 3-part composition, both of which are exactly 2-dimensional, displaying the data exactly. They both have vectors for the 3 fatty acid groups emanating from the center. The CA biplot is straightforward to interpret. Each direction defines a biplot axis for SFA, MUFA and PUFA parts, onto which the species can be projected to line them up in terms of their exact compositional values on the respective part. The LRA biplot is interpreted differently. The CLR direction itself is not of direct interest. It's the links between the CLRs that represent the log ratios. So this arrow from CLR PUFA to CLR SFA represents the log ratio log of SFA over PUFA, and so on for the other 2 ratios. The species can be projected onto these biplot axes to line them up, again exactly, on their log ratio values. And given the 3 log ratios, it is easy to back transform them to their original compositional values. Now, if you transfer these links between the CLRs, so they emanate from the origin of the biplot, this is exactly what you would have obtained if you did a PCA of these 3 log ratios. And if the ratio A over B is inverted, the biplot arrow will simply just be pointing in the opposite direction with the same length. Remember, log B over A is equal to minus log A over B. Doing a PCA on the CLRs is just an efficient way of analyzing all their pairwise differences, that is the PLRs, the pairwise log ratios. Now comes one of the main messages of my talk. Notice again that the CA on the left is rather different from the LRA on the right. Now let's keep the LRA on the right hand side and perform the CA on the 4th rooted data on the left. Now the 2 configurations of the species are much more similar. Now do the CA of the data to the power 0.1, that's a 10th root transform, and the figurations are practically the same. You can see where this is going. At the limit, the CA converges to the LRA. You probably didn't notice on the scale values of the axes that the plot of the fish is shrinking as the power goes down. So it needs to be scaled up to converge exactly to the LRA. And this is where the Box-Cox transformation comes in. Here's the Box-Cox transformation, and since it converges to the log function, and since both CA and LRA double center the data, the result is no surprise. The scaling by 1 over the power lambda is what brings the shrinking configuration back up to correct scale. Since benzocarie is CA and Aitchison and Louis are LRA, this makes a pictorial formula. The limit of Box-Cox of benzocarie is Aitchison and Louis. Or what about the George David function that anglicizes names? The limit of George David of Jean-Paul is John and Paul. Absolutely amazing. Going back to the minerals data again, we can show this convergent in an animation. We saw that the regular Ca was noticeably different from the LRA. I now show an animation for powers descending from 1 to 0.01 in 100 steps of minus 0.01. So it goes from 1, 0.99, 0.98 and so on. For power 1, it is the regular Ca at the start, and the last slide is the LRA limit as chi power converges to the CLR. So here goes the animation. And you will see the last slide when lambda equals 0 switches to the LRA limit. You can watch that a second time. Realizing that this will go further than dimension reduction and also be useful for other statistical methods, I have defined the chi-power transformation, which is a combination of the Box-Cox power transformation and the chi-square standardization in Ca. This is the R function where you can see the elements of this combination, and also that, as I have defined it, it can be organized to converge to the CLR transformation. On the right, for the minerals data, at the top, here are all the chi-power values with lambda equals 1 versus the corresponding CLR values. And then, in the lower plot, the chi-powers with lambda equals 0.1, the stronger root transformation versus the CLRs, and you can see how close the agreement is becoming. Okay, and now back to the fatty acids. These have several zeros in the dataset, which are trace amounts below the detection limits, and clearly the log transform is inappropriate. But the chi-power transform is okay for a while, until it breaks down as it tries to converge to a log. The idea is to find a power lambda which comes as close as possible to the CLRs. One way is to define a target LRA where the zeros have been replaced. One way is to replace with 2/3 of the lowest detectable value, x min, for each fatty acid, which is the mean of this triangular distribution from x min down to 0. There are two ways to help with choosing the power lambda for unsupervised learning, such as PCA and clustering. The first is to check the isometry of the samples. On the one hand, we have the log ratio, thanks to the zero replacements, which we've just done, and on the other hand, the geometry of the chi-power transform data. Procruste's analysis allows us to measure how close the chi-power geometry of the samples is to the log ratio geometry, which we can do for a series of lambdas. The other criterion is the coherence of the parts. Subcompositions can be chosen, reclose to sum to 1, and then again use Procruste's analysis to measure how close the geometry of the parts is in the subcomposition to their geometry in the full composition. Thus, checking isometry is by correlating geometries of the samples, whereas checking coherence is by correlating geometries of the compositional parts. Here are the Procruste's correlations for the samples, showing that the best we can do is to use a power lambda equals 0.8 when the correlation is 0.925, and then it goes down rapidly as the power decreases. This correlation is measured in the full space of 14 dimensions in this case, one less than the number of fatty acids. The PCA of the chi-powered transform data on the right is shown next to the LRA on the left. These are both contribution biplots, showing that the three main fatty acid drivers of the solution, 22,6, 25, and 18,1, are the same in the two analyses. The positions of the species in these 2D plots are similar, but remember that these are 2D projections of higher dimensional configurations. Alternatively, checking the coherence means comparing the geometry of the parts in subcompositions and compositions. Because the number of parts is not large, we can compare with the worst case of subcompositions with just 2 parts. and the Procrustes correlation for the power lambda equals 0.8 is at least 0.982. We could also do this for a series of lambdas to find the lambda that gives the highest. What does worst case mean? A two-part composition takes just two fatty acids, expresses them as proportions of just these two, and then computes the chi-power distance between the parts, and compares that with the chi-power distance of the two parts in the full composition. To close off the unsupervised learning methods, here are cluster analyses of the CLR transform data, where zeros have been replaced, and the chi-power transform data, where zeros have been maintained. There are similarities, but the results are not the same. It can be argued that the method on the right, which does not change the data, is the preferred one, compared to the method on the left that changes the data to suit the log ratio approach. The parts themselves can be clustered. Here, rather than clustering the CLR transform data, I prefer to do what I call amalgamation clustering, simply adding the parts together at each step. This is more intuitive than merging CLRs and is the same idea as in correspondence analysis. The log ratio variance is still maintained as the clustering criterion, and when two parts are merged, log ratio variance is lost. So at each step, the two parts that give the least loss of log ratio variance are joined. At the end of the agglomerative clustering, all log ratio variance is lost, so the topmost level is the total log ratio variance, 0.308 in this example. Cut points for either 6 or 4 clusters are indicated here. Finally, I want to briefly illustrate supervised learning using log ratios. I don't know if vitamins have anything to do with fatty acids, but there is some evidence of a connection. If you put all the pairwise log ratios into a regression tree algorithm to predict the level of vitamin B12, you get one split based on log 16.1 over 18.1. Basically showing the right-hand split that if 16.1 increases and or 18.1 decreases, then vitamin B12 is predicted to increase. Now, using the stepwise linear regression with a conservative stopping criterion, as advocated by Kunders and Greenacre, 3 pairwise log ratios are selected, and indeed the first one chosen is log 16.1 over 18.1. It has a positive coefficient showing the same direction of effect that I just observed in the tree. These 3 log ratios are non-overlapping because no fatty acid appears more than once. Any linear combination of log ratios will be equivalent to a so-called log contrast, which is a linear combination of logs where the coefficients of the log contrast sum to 0. This slide shows that if you consider a very small increase in a part, say a 1% increase in a fatty acid in this case, you can think of the log contrast coefficient divided by 100 as the effect of that 1% increase on vitamin B12. So that 3.54 coefficient of log 16.1 that you see in the regression is equivalent to a 0.354 increase in vitamin B12 per 1% increase in the fatty acid. The log contrast effect sizes can be plotted as negatives and positives in a bar plot on the left and with confidence intervals on the right. And note the confidence intervals don't cross the null hypothesis of 0. The observed versus predicted values of the model show a moderate agreement with r squared equal to 0.5. The scatter plot is enlarged here. An interesting exercise is to regard lambda as a tuning parameter for the regression analysis, running through a series of lambda values and then applying the same style of variable selection algorithm to predict vitamin B12. We use the BIC criterion as a stopping rule. On the left, we see the major improvement achieved at lower values, with a minimum at lambda equals 0.21, practically a fifth root transform. The discontinuities are due to different numbers of predictors being chosen. The 5 fatty acids are chosen when raised to the power 0.21, and the regression improves from 50% variance explained, as we had before, to 72%. The predicted values are improved, shown here. That's the end of my talk, but some things to remember. Aitchison-style coder using pairwise log ratios, or PLRs, centered log ratios, CLRs, or additive log ratios, ALRs, ensure subcompositional coherence. The choice depends on the objective, and care is needed to interpret the results. Zeros are a big problem for coder. I have called them the Achilles heel of coder. Usually the data are changed to adapt to the log ratio approach, but the quest is to find methods that adapt to the data. For example, the Box-Cox power transformation combined with the chi-square standardization, that is the chi-power transformation, is a valid alternative to log ratio transformations and needs no zero replacement. The power lambda is chosen to maximize isometry and subcompositional coherence, or for supervised learning to improve predictivity, as just shown. It is quite amazing how correspondence analysis chi-square distance, fine-tuned with a suitable power transformation, can find validity and applicability in the field of compositional data analysis. Thank you very much, and here are some of my recent publications that are relevant to this presentation. This is the conference dinner in a bar of the Sensometrics 2024. I hope you enjoyed my talk. Having a great time here.